Let's go back in time to the start of the early universe. When it was forming, matter and antimatter formed in equal amounts. And when they meet, they annihilate each other, leaving nothing behind but a ton of energy. But if you take a look around you, everything that you can see is made up of matter. So what can explain this huge inequality? The answer to this question may lie in a theory called leptogenesis. Physicists have compiled all the fundamental particles into the Standard Model. In the Standard Model, there are two main groups of matter that are most important for leptogenesis. These are quarks and leptons. Quarks make up protons and neutrons, which themselves are part of a group of matter called baryons. Leptons, on the other hand, consist of electrons and neutrinos, ghost particles that don't interact with any form of matter. Now, all of these particles have their antimatter counterparts. For example, the electron has a positron, and the proton has the antiproton. But the heavier cousin of the neutrino, the right-handed neutrino, has a weird property that it's its own antimatter particle. Okay, now let's take a look at leptogenesis. First, at the hot dense conditions of the early universe, all of the particles in the Standard Model exhibited completely different properties than what we can see today. For example, the mechanism that gave these particles their mass didn't exist, and so they were all massless. Second, at less than a trillionth of a second after the Big Bang, some of the antimatter leptons were converted into matter baryons, and this is what causes the matter-antimatter imbalance that we can see today. Let's return to those right-handed neutrinos. They can sometimes break down into a lepton plus a force-carrying particle. But the thing is, they usually break down into an antimatter lepton. Now, you may be wondering, if it breaks down into antimatter, don't we want matter? Well, we do. You see, in the universe, there are several conservation laws, like the conservation of mass or energy. Similarly, there's the conservation law for the lepton and baryon number. The lepton number is just the sum of positive matter leptons, +1, and negative antimatter leptons, -1. The same goes for the baryon number. And the rule states that this number has to stay the same before and after any particle interaction. However, when the universe was hot and dense, the only thing that was conserved was the baryon number minus the lepton number. Let's take a look at how this works. If you have one antimatter lepton and 0 matter baryons, the B minus L value is 0 minus -1, which is 1. And if you have 1 matter baryon and 0 antimatter leptons, the B minus L value is 1 minus 0, which is still 1. And it's because of this, since it's not in violation of the B minus L law, that matter baryons were converted from antimatter leptons. And this is a scale-around process. Let's summarize. Today we saw that the heavier cousin of the neutrino, the right-handed neutrino, can be both matter and antimatter. It tends to decay into an antimatter lepton, which is then converted into a matter baryon through the scale-around process, giving us this matter-antimatter imbalance that we can see today. So remember, when you go outside and see something beautiful, you have leptogenesis to thank.